All right, everybody, we are going to be doing some spectroscopy today. And as exciting as organic chemistry 2 is, I am not thrilled about all of the physics in this chunk of our lecture. So spectroscopy embodies the idea of establishing or trying to identify a molecule based on the signals that come off of a spectrometer. So what happens is we shoot light, aka photons, aka radiation, in a pretty little line at other particles. And we refer to these particles by their nuclei because that's what we care about the most. And they are surrounded by a magnetic field, aka B naught, but I call it Bo. So if you hear me call it Bo, then I'm saying it wrong, but it's cute, so don't worry about it. There are different kinds of spectroscopy. There's infrared, UV vis, and NMR, and we care about NMR, at least in this lecture. So in order to understand why spectroscopy is important, we need to know a couple relationships. So wavelength and frequency are top two priorities, basically. If you know that their relationship is indirectly proportional, you're already halfway there. You already know half of physics. Not really, but anyways, so if you know that these are indirectly proportional, then you can also know that if one of them's going up, one of them's going down, vice versa. But our main thing that we care to compare involving a spectrometer is frequency, energy, and strength of the magnetic field, or Bo. That's what we care about. And all of these values, so I gotta draw straight lines. Oh, JK. All of these values are proportional to each other. And this little relationship gets a pretty big box because if we know these relationships, then we can basically determine how spectroscopy matters. And as we keep going, keep in mind that photons are little packets of energy. Energy is important. And protons are like little magnets. That's what my teacher says. So keep that in mind. And the kind of spectroscopy that we're going to talk about today is NMR spectroscopy. And NMR stands for, nuclear magnetic resonance. And this kind of spectroscopy specifically refers to hydrogen, protons, or we could also use carbon-13 as our isotope. And different isotopes do different things, but what we really care about right now is our hydrogen ones. So what does a spectrometer even do? Like, bro, what the hell is that? So in the real world of science, there are electrons everywhere, and they're, doing their thing, and they are surrounding these protons that are a part of molecules. So all of these protons have spins, and without a magnetic field, they're not oriented any certain way. They're just literally vibing. But when we want to determine the identity of these compounds, these unknown protons, then we can stick them in a spectrometer, big word, stick them in a spectrometer, apply the external magnetic field, and now all of our protons will be either aligned, like this, because up is aligned, at least in this example, and down means that they're not aligned. So I had 4 protons over here, so I'm going to draw 4 protons over here. And you can see that in my example, I have 3 protons going with the magnetic field and 1 proton going against the magnetic field. And this concept is really important. So if a proton is parallel to the magnetic field, it is more stable. And this is all very relative, so don't quote me, for real. But if a proton is anti-parallel, it is less stable. And this is referring to the spin states. And a spin state is a value that we quantize to let us know if the proton is going with or against a magnetic field. If it's going parallel to the magnetic field, then that means that its spin state is at positive 1/2. That looks ugly. But if it's anti-parallel, then it's going to be negative 1/2. And this idea is really important because after we stick these lovely protons, I was not going to say lovely protons, into a spectrometer, as the magnetic field increases in strength, we have our 3 protons that are on the lower energy level, and we have 1 proton that is on the less stable energy level. Just going to put everything in the same screen so you know what I'm talking about. We had 3 protons that were parallel, 1 proton that was anti-parallel, but after we shoot radiation at this at these particles, then what happens is one of these particles gets really excited. It's literally called excitation, and it's going to go into the higher energy state. It's going to switch spin states. And we care about this level of energy because we can't shoot radiation at these particles unless the radiation is at the same energy difference between the spin states. So that was a lot of content, but I'll write it down. So we have to supply energy, the photons, at the same level as the difference between the spin states. So this is me shooting light, photons, at our particles, and this energy, since energy equals Planck's constant times frequency, this is what I'm going to refer to as our photons doing their thing. And then after the excitation happens, then instead of having 3 protons in the lower level, we're going to have only 2, and then we're going to have 2 in the higher energy level. And you will see that there will normally be more protons in the lower energy state, this state, because it is more stable. And after excitation happens, we see that this movement shoots off a signal, and that's how we're able to tell what the identity of the compound is, because of the signal that's given off. And that is a lot more science than we're going to do today, but let's just keep going. So there's this thing, upside down fish, called the magnetodrag ratio. Oops, not ratio. You can see it as Magneto, like from X-Men. Love him, bad guy. So the magnetodrag ratio is the susceptibility of protons / nuclei to the external magnetic field. And before we go into what we're doing, I'm going to introduce the NMR equation, the nuclear magnetic resonance equation. Really important. So what we have is that Planck's constant times frequency, that's a V, sorry, equals energy, which equals the magnetodrag ratio times H times the magnetic field over 2 pi. So we're going to establish some relationships knowing what we know about this right here. So if energy increases, since the magnetodrag ratio and energy are both quote unquote on the top, then as energy increases, the magnetodrag ratio will increase. And we already know that as energy increases, the strength of the magnetic field increases. And we also know that the relationship between energy and frequency is direct. So if you can put all of these concepts together, then you literally know, like, basically all of this cute little lecture that I'm doing. So this concept is really important, but you're like, bro, what is the magnetodrag ratio? What is it? This symbol, just to let you know, is called gamma, but I call it my upside down fish. So if me and my girl are going out, there's me, and here's my girl. If we're going to go out, we're going to go get lit, and we each have our own magnetodrag ratio. If my magnetodrag ratio is higher, that means that I am more susceptible to the outside world of dating. And my girl, she's taken whatever. Her magnetodrag ratio is lower than mine because she's less susceptible to the external magnetic field, aka the world of dating. So since my magnetodrag ratio is higher, I have more energy going into the dating world. I am more susceptible to the external magnetic field, so I have a higher level of energy when I go out. And my girl, she's just going out because I'm trying to have a good time and she wants to spend time with me. So sweet of her. Her magnetodrag ratio is low because she's not as susceptible to the external magnetic field because she's taken whatever. So her energy level is lower when she's going out. So if you think of my little analogy when you're trying to determine these relationships, hopefully that will help. So some values that we need to know for the math problem that we're about to do is this. So these are the magnetodrag ratios for hydrogen 1 and carbon 13. Carbon 13 is an isotope of carbon, and an example of how we know that carbon 13 is more susceptible to protons, just kidding, more susceptible to the external magnetic field, is that carbon 12, in comparison, has a magnetodrag ratio of 0. It is the most stable carbon isotope because it is not susceptible to the external magnetic field. Okay? Lots of words. Sorry that I talk fast, but I get excited. So this is our equation for the magnetodrag ratio. That is my upside down fish. Sorry. It's the ratio over 2 pi. And for hydrogen, it is 42.576 megahertz over Tesla. And for carbon 13, it is 10.705 megahertz per Tesla. So keep these numbers in mind. I'm about to do some science. So I'm going to move this up a little bit so we can still see our values, still see me and my girl, but we're going to do a practice problem. What will be the carbon 13 frequency of an NMR spectrometer that operates at 100 megahertz frequency? Okay, so before we do this problem, we have to combine the relationships that we had up here. And, sorry, I will point to what I'm looking at. So with this equation, we have a kind of combined equation that can allow us to compare the frequency, which we need to find, frequency of an isotope, frequency of the spectrometer, and, oops, I forgot a little part of the problem. That doesn't even make sense at 100 megahertz frequency. What even is that? I'm so sorry. Okay, at 100 megahertz for protons. Okay, sorry. So we combine this equation up here, my little green highlight, to form this equation, that frequency equals the magnetodrag ratio over 2 pi, that's this value that we're given right up here, times the external magnetic field. So what we need to find is the carbon-13 frequency. We know that we're using the same spectrometer, but for protons, which means our hydrogens, our frequency is 100 megahertz. We don't know the strength of the external magnetic field, but we don't need to know that. So let's create two different equations. We're going to create an equation for the carbon-13 and then also for the protons. So here's my hydrogen equation. 2 pi times the magnetic field, and we're going to plug in the values that we know. So the frequency for the hydrogen is 100 megahertz. Our magnetodrag ratio value is 42.576 megahertz over Tesla, and we don't care about the strength of the magnetic field. We don't. So for our carbon-13, same exact equation, we're going to plug in the values that we know. We're trying to find the frequency. We know this value because it's 10.705 megahertz per Tesla, and we still don't know the strength of the magnetic field. So this is a basic algebra problem, or you can do a little bit of quick math and find this out with a really strong guesstimate. So what we see is that in this equation, we have two unknowns because we have the strength of the magnetic field and a question mark for our carbon-13 frequency. In the top equation, we have one unknown. But in algebra, my favorite thing, not really, but my favorite thing in this lecture is that if we put two equations over each other in a fraction, then we can make a proportion. Because if we have the same thing on the top and bottom, we can just cancel it out. And then we literally have a proportion where we can cross multiply and do some quick math. And what I see is that 42-ish divided by 10 is about 4. So if I'm going to divide 100 megahertz by a factor of 4, then my question mark will be about 25 megahertz. So before we actually do the problem, and we actually do all this math, we're going to see if that makes sense. So hydrogen has a higher magnetodrag ratio. I'll point to what I'm looking at. Hydrogen has a higher magnetodrag ratio, which means that it is more susceptible to the external magnetic field. Since it is more susceptible, that means that as its magnetodrag ratio increases, its frequency will increase. So its frequency is 100, its ratio is 42-ish. Let's talk about carbon. Its magnetodrag ratio is 10-ish. So it makes sense that if its magnetodrag ratio is lower, then it'll have a lower frequency. So if you can't make that conclusion by yourself on the first try, totally fine. Take some practice. And if making a ratio, making proportion is like, bro, Sophia, I want to see the facts. I want to do the math. I want to make sure I'm doing it right. We're going to do that too. So it's good to be able to get to here, but starting with the math one by one is what I do first. So here's the actual math of what we're going to do. What we can do, since we have only one unknown in our first equation, is we can solve for the strength of the magnetic field and then plug it into the next equation, because the same external magnetic field will be used because we're using the same spectrometer. Each spectrometer has its own strength of the magnetic field. So if we're using the same, different molecules but in the same instrument, then it's going to have the same external magnetic field. So if we just divide 100 by 42.576, because, try to isolate the magnetic field on its own, then we get that the bow equals 2.35 and some change Tesla. And now that we know what one of the unknowns is in our carbon-13 equation, we can do our second problem, where we don't know the frequency of carbon-13, but we do know that its magnetodrag ratio is 10.705 megahertz per Tesla, and that the strength of magnetic field is 2.35 and some change. And then we do some multiplying, and we get 25.16 and some change megahertz. And that's pretty damn close to 25. I'm not gonna lie. Sig figs, whatever. But even though this problem is kind of like a beginner problem, it's kind of tough because you're seeing all these new words, all these new weird upside down fish, but taking it one step at a time, recognizing your relationships and things that you know, then it makes it a lot easier. So the first time I did this problem, I was really confused by the ratio. I was like, what is that? What are you doing? But doing the math on your own can make it make a lot more sense. And then you can tie conclusions by yourself, and you'll be able to figure out that if you compare any two molecules in the same spectrometer, all you really have to do is compare their magnetodrag ratios to determine the frequency of one given the other. So what we covered was the magnetodrag ratio, how to use that in a problem regarding frequency, protons, and we also talked about what exactly happens in an NMR spectrometer. And then we talked about relationships. These are really important, so if you didn't understand anything in this lecture besides these relationships, then that's fine, because if you get this, you got half of physics down. No big deal. If you have any questions, feel free to leave a comment, like, and subscribe, LOL, and I'll see you next time.